There we go.
Nice.
We are live.
Yeah, so just check the YouTube as well to see if it's.
I can check it. We can check, your voice again here. Say something.
Deep learning.
Guys, should we take a seat? Start up.
Ready for soon going to present something? Now, we're supposed to talk
No guest Wi-Fi,
like
actually.
General office Wi-Fi, so we try to, set up another network.
No, we need to do that for next time.
Yeah, maybe we should not do that. but I think, we are progressing, so next time probably Okay, don't worry, we have still some foldable chairs.
And yes.
So before even saying welcome, I have to say that we are recording the presentation as I wrote in the page, and it's just there, and it's also now online in YouTube, and we will have most likely some also online audience in Google Hangout. So welcome. Every now and then Roelof writing me the number of people, reminding me with some screenshot how many people are joining to the meetup, and it's super amazing because we started very small. I think first meetup was 40 something people. The second meetup was 86, and then now we are. In the morning we were 123. I don't really like, when people start talking about numbers and how successful they are. I don't mean at all to talk about that. I am just very glad that we are growing, and we are building a very good and nice community. And we have good volunteers to present, already many, and that's nice. And I'm happy because I also learned a lot of things and meet new people. Cheers to that. And then many of you are new, so I would like to welcome you even more, and also appreciate those who are coming back. So this is the third meetup, and for those that haven't been here, we thought of starting the meetup and having it as much as we can, but we are trying to, being good at keeping the habit of having 2 meetups per quarter at least. Well, currently, in Meltwater we initiated this, but if any company, university would like to host one of the events, of course we would be really happy. So just let me know. And so the first meetup we had UC Carblen with a very nice high-level presentation about NLP and big data, and like more looking at what it goes in future and what is going on now. And then the second one we had about name entity recognition, looking at the applications and the challenges. That was presented by me and Bhaskar. He's in a meeting currently. He can join us soon. And today we will have Roelof. He will present about deep learning, an introduction, and also with focus in NLP. We are hoping to have more sessions of deep learning that we can get something out of it, so maybe doing something together, defining something, and yeah, let's see how it goes from there. And Roelof, we met in several meetups, and he's a PhD student in KTH, also CTO of a startup company, Feeda, right?
Yes.
And his background is in deep learning, as you know about this presentation, and graph-based and NLP. And what did I miss?
Actually, I have a background in anthropology.
Yes, of course. And yeah, so we will have Roelof to present. Before that, I would like to spend a few minutes also talking about what we want to do. So I think this is a very great idea and a great initiative from Roelof to have an online streaming. So far, we had everything recorded offline and put it on YouTube offline. So we try to keep this habit. And then, okay, let's see what's going on here. So this is the meetup page, right? And so in the meetup page, there is this site where you can see, you can have access to slides from previous presentations. I put in each of the meetups also a link to the YouTube page, but I think maybe it's good to have our own page because it's not that user friendly to update people, let's know what is going on. So for this reason, I also have it's a bit confusing here for me, but just bear with me for a moment. No. Okay. Hold on. No, seriously, I have a meetup page. Wait. I think I had a meetup page. Yeah, anyhow, I have to make this.
Isn't the left tab there?
No, it didn't work. It went to Sahara as a page, but okay. I can show it to you later. There we go. So far, I haven't done anything in this page, so I don't know that much of what's going on here. But I'm going, to put. If anyone wants to, put an interesting link or suggest any reads or having a question, we can have more interaction. I'm going to share this link. Then we will have a more active community. So let's forget about these boring discussions and have Roelof presenting about deep learning. Thanks.
Bear with me. Yeah. Okay. Yes. So, welcome everyone. Thanks again for Sahar and Meltwater for hosting today's meetup. So Sahar already said, I'm a PhD student at KTH, part-time. That's called Industrie Doctoraat. And also I work for a local startup here in Stockholm called Feeda, where we do social media aggregation. And there I also work as the main data scientist. And there we basically apply deep learning to data. So yeah, when Sahar asked me to give this presentation, of course I said yes. It's always nice to tell about something so hot and something I'm very excited about. But also it's a bit difficult always to estimate, like, what is the audience, what do people know already. I presume that most people here are already quite well aware of like machine learning as such. I do have like a short introduction still into machine learning because there were some people asking for that. But we'll go through it quite fast, just so we have it also in the slides and it has some things to return back to as well. And for the rest, feel free to interrupt me if you have any questions or clarifications. Or if I have to speak louder, I still have a bit of a cold, so bear with me for that as well. But the slides are also online already, so you can see them here, so you can just go ahead and read with it. The presentation will be two parts. In part one, we'll go through the general, some machine learning and deep learning, architectures, history, etc. Then we have a short coffee break, I guess. And then in the second part, we'll actually do some live coding. And we'll start developing two deep architectures. First of all, well, which was one of the first, deep convolutional network, and then also some other variants. We'll see more about that. So deep learning. Deep learning is everywhere in the media. You read about it. Companies doing deep learning, startups. It has revolutionized many things. You see it everywhere. This is just from 1 month. I think it was last November, when I just randomly chose some newspapers and blog posts, and this is all. Understand emotions. Spotify generating better playlists than you can. Intelligent robots. So the idea with deep learning is that it's magical and it's like a unicorn, we data scientists like to call. It's going to solve everything. We'll all be, out of a job. We'll be all sitting at home. Computers will be doing everything for us. There will be self-driving cars, etc. Luckily, this is, at least for us data scientists, this is not the case. Deep learning algorithms will also not take over our jobs, but they do perform much better in certain specific tasks. And we actually don't really know yet much about what is going to happen further, because it's still a very under-theorized discipline. There's a few people who have a lot of assumptions, and we'll see more about it, and they know what they're doing, but the rest of us, especially if you're starting out with your PhD as a graduate student, you have to kind of follow up what is going on, and you find out that a lot of these things are not so much theorized at all. It's just very empirical in a sense, or more from experience. So deep learning, yes, it's an ongoing trend. So how many people, first of all, have heard about machine learning? I hope everyone, yes. How many people are using like machine learning in their job or on a daily basis or whatever? Around maybe half. How many people know how to use or are using neural networks? How many like them? Deep learning. Are there any more deep learning people here? Yes, one, two. It's hard to also see what is deep learning and what is not. I think if you want funding for your project, you better call it deep learning. A lot of times it's not the case. Like, I will not show actually that much about NLP because it's really hard to do deep learning on NLP. And I will explain more about that, why this is the case. So I wanted to just first go through the general things, and I will show a little bit of the things which you can do with deep architectures. But a lot of the work which is done actually in language technology or natural language processing is actually not deep learning. It's called like that, but we'll see that this is not the case. So deep learning. First of all, as we all know, it's brain inspired, so it's a model and a highly unrealistic model, but a kind of useful working model of the brain. Neural networks are also just that, but we'll see more about what makes deep learning so different. But first of all, it's a vision, and the three guys who came up with deep learning actually call it also conspiracy publicly. They call it a conspiracy of they themselves making neural networks sexy again. But the idea is at least that it makes algorithms better and easier to use, so it actually makes it more simple. And it also has like revolutionary possibilities for all kinds of machine learning and AI practical applications. So deep learning is a subfield of machine learning. Learning is biologically inspired. So this is the model which is used. So this is some of the different quite useful ways of thinking about it as well. There's a field of AI, which is not so much used anymore since the AI winners multiple times that all the funding has been drained. So now we instead call it machine learning. But AI as a kind of field is actually busy about intelligence. So what makes computers intelligent? And especially what is knowledge for computers? How can you understand the world? And how can computers understand the world in a way that is useful for them? So how can you construct knowledge in a representative way for computers? So that's kind of how I see AI. And machine learning is just a way and a more mathematical approach of how you apply mathematical models to this kind of idea. And then there's also representation learning, is another subfield which is quite useful to think about it, which is more about when there's this huge pile of data, how do you represent it to computers? So not only make it understandable, but also make it kind of give useful results as well. So the impact of deep learning has been huge. And we just show a few examples. We all know like Watson and we know other kinds of things, but this is just a Microsoft speech group. So this is when they started to apply deep learning, and immediately the accuracy or the error rate went hugely down. And this is kind of what they had been doing for all those years. Not much was changing. And I could easily grab like anything for many other fields. I could have done the same for NLP, and would end up here maybe 2012, 2013 instead, and it would also be kind of even longer. It would not be 2000, but it might be 1990 as a line almost like this, where ground clusters or SVMs have kind of ruled since the 1890s, or conditional random fields maybe, but it's kind of, yeah, any, no?
100% error in the beginning.
Yeah. This is, I don't know. That's probably when they started. Someone was really sucky in that department. Yeah.
What is switchboard?
What is switchboard? It's a data set. It's just a switchboard data set of like, people, when you call persons, and okay, how do you transfer? So it's a data set used for audio recognition, for understanding speakers. So more deep learning for the win. One of the biggest, what gave the biggest impression that it was done mostly with computer vision was the German traffic sign recognition, which was the first deep net. It's won the competition, and since then there have been many more, but these were the first ones, which were kind of internationally recognized, handwriting recognitions, etc. And again, these things are all based on the kind of abstract notion of the brain. So what about machine learning then? So machine learning, as a field, deals with the construction and study of systems that can learn from data, as well already said. And most of us who have been studying machine learning, we all know this classical, very boring definition from Mitchell. So computer programs have to learn from experience with respect to some class of tasks, T, performance measure P, and that's kind of it, and then it's a repetition of that. But important here, again, is just the fact of experience, that machine learning as such deals with knowledge, with experience, and the idea is that when you have data, or a lot of times there is all kinds of implicit notions which you don't really know how tasks should be solved. And that's why we use machine learning, because we don't even know. There's a lot of implicit assumptions we have ourselves. So we cannot really make them explicit to the computer. So the idea is that we solve this by giving just a lot of examples, with a lot of data. Then the idea is that the more data, the better. But there are a lot of limits with how much data you can actually work. So then, in traditional programming, where you have data in a program, and kind of the computer makes the output, with machine learning, the opposite is true. You try to come with data, and you also try to come up with what you want as the output, and then instead the computer comes up with the kind of program. Let's just skip through this. If there's people who want to know more about machine learning, but for now, let's just say that the main concepts of machine learning we'll be using is that the representation, which are the algorithms you use to kind of train on your data set. Evaluation, which is a way of all kinds of different metrics, from mean square error to whatever, to kind of evaluate how your algorithms are performing. And optimization, which is kind of what you do afterwards, where you try to optimize what you already have. So you think, okay, it kind of works. How can you make this better? But then the traditional approach for both computer vision as well as natural language processing is, first of all, you start gathering as much labeled data as you can get. So this is the clear, but both unsupervised and supervised. You still want as much data, supervised you want it labeled. And then you throw in some algorithms, and we NLPers, at least in my experience, we like to just throw in some SVMs. That's kind of the end of it if it works. That's the standard to maybe try some random forest or something else. But okay, if we try more than those, then we can choose. So we will pick the best one where the evaluation metrics we have kind of gives the best result. And then the actual work starts, which is spending hours and hours of hand engineering features. Or if we see it like this, we have the data pool. And we have manually annotated data. And this is what has been one of the main things NLP has been working with. Is manually annotating huge data sets, like millions and millions of sentences, and we try to annotate the grammar, and we try to annotate whatever we can about it, the entities, or whatever. And this is how we have been doing like breakthroughs for many, many years, mostly up till now. Just by really working manually on kind of trying to understand like morphologies of language or whatever. So that we feed into the learning algorithm. And some of these are, for instance, the PEM3 rank, which is around 2 million sentences words, and manually annotated on the corpus of this corpus of WS again. It's like the Times, Wall Street Journal. So this has been like for many, many years. And I have another graph which I took out, like how long it took to annotate this corpus of like millions of features. But it's an insane amount of work by many, many research, and not just research. It's highly specialized field for people with highly skilled knowledge. You kind of really have to know language well to make decisions about when sentences are constructed, like what to choose. Another problem with this is that it can be highly ambiguous as well. So even linguists will not be able to make perfect part of speech tagging sentence because the context might be missing or whatever. So this is, for instance, an example of PEM3 ranks for one sentence and how it's annotated. So yeah, that's a lot of work. And of course, this is also not like really scalable in the sense that we want to work with data which is growing insanely much with big data that we have to manually annotate. It's of course not possible. So we have to find a different way of doing it. So we have to do it in some way automatically. We cannot like keep manually, making our features or manually handcrafting our features. And one problem also with that is, for instance, here we know that there is this thing of polysynonymous words or disambiguation. This doesn't always work. The word fruit flies like a banana. It's a classic one. There's a lot of different ways how you can interpret that sentence and how you can post-tag it. But there's only one way how you can annotate it, which you say is the correct one. And then you have to use a lot of tricks, and you can use a lot of tricks to kind of make exceptions, and the rules grow and grow and grow and grow. In this case, yes, it's like this. In that case, it's that. And we start from a very simple annotation. It becomes even more complicated. And then our algorithms also have to deal with that, which becomes almost impossible. And we get really weird outliers. Or for instance, in also the Wall Street Journal, from the PEM3 data set, there is this, I think there's a few times that the word banana figures. So one time it's just mentioned as a noun, banana. But another time it's mentioned as going bananas, which is very different. And this, both times that it's mentioned in that way, it really kind of mixes up when you try to use bananas, try to post-tag bananas with feedback. 50% of the time, like half of the time, it kind of mixes it up. So that's the problem of finding representative data as well, which can again be only solved by more data. More data you have, the less outliers you have. But again, we cannot manually annotate all of it. So again, we all know we instead of data as such, we make a separate training set, We make a test set. Most people make also a depth set, which we keep separate from any of the algorithms just to later test. And we feed the training set into our learning algorithms. We get features, or we manually construct the features. We get a classifier, we do some predictions. It can be good or it can be incorrect. And we go again and we use a test set as a separate way, not to actually train the algorithm as such, but more as a kind of continuous loop for feeding it to keep working as a separate kind of way. Another problem with this is also not how humans learn. If you want to think of like, okay, how can you make computers learning, especially if you take more biology as an inspiration. Humans learn things in a hierarchical way. So we start with simple X, and everybody who has a toddler knows that we first start pointing at things and we start to know, okay, what is this, mommy or daddy? Now does it look like? And then we start combining things together, etc. So we start with first learning simple concepts and then using these concepts together to build more complex ideas or combining complex concepts. So as for machine learning for NLP, again, until at least the early 90s, almost everything was manually handcrafted. And for instance, it's in many cases still a state of the art. So it definitely has been really, really successful and very useful as well. The Berkeley parser is it's much better than Stanford parser. People might disagree, but generally it has better accuracy. Or the Stanford parser is a much more probabilistic idea that uses much more unsupervised models and not some is annotated as well, but it's not completely manually crowded as the Berkeley parser. So then, yeah, more data becomes available. And of course, then we have to do something. We cannot keep up with our annotations, so we have to find a way to automatically kind of construct knowledge from this kind of data. And that's when most NLPers at least switch to pure machine learning-based approaches. And another good thing on machine learning in that sense is also that they supposedly should be more robust, and that they have a better coverage of the world training as well. So, having had all of that about machine learning, we continue with neural networks. Are there any questions till now, or please?
One question. Can we say that like Berkeley that is more like a static system compared to Stanford? Stanford is more easier to be generalized or extended to other languages compared to, because it's probabilistic compared to less expensive.
I mean, Stanford parser is moving more and more in the direction of, for instance, using recursive neural networks. It's one of the things which kind of, if you look at the core NLPs, like the main parser of Stanford, we're building more and more of these kind of things. So it becomes, that's it becomes easier to use and there's a better coverage as well.
But the payoff is that it has less accuracy.
Well, yeah, the payoff is that it's more generalistic, which is kind of a good thing, but then again, in certain highly optimized parsers, I mean, they of course will be able to perform better and very specialized tasks. Yeah, so it's a trade-off. So, starting with the perceptron of Rosenblatt, which was one of the first ideas of using brain-inspired approaches, and which was then kind of killed off because it supposedly wouldn't be able to use the great XOR function. There's a famous book written on that. But some of the things which it kind of could do were still quite impressive. If I can. For instance, this is pure note. You don't see it? So this is, I think, 60s or 70s. That's 50s, or probably 60s actually. So this is a very, very naive and one of the first neural approaches. And I think it's on one layer, so it really cannot do so much. But some of the things it can do is recognize genders within faces. So first you will see Rosenblatt, you will see creating the right. So he says there's a man, and it's correct, and he feeds a picture into it, and kind of debugs it, and trains the network. That's it. No, doesn't. Yes. Yeah, you get the idea. So at least it's pretty impressive, if you ask me, especially for that time, and especially since it uses a pure, not even multi-layer perceptron, just so yeah. Back to the perceptron. So here we have a more schematic. You have up to, you have some inputs. This is of course again modeled on this idea that there is a neuron, like your brain. And basically it takes several binary inputs, so it can be, it can be 1 or 0, and it also produces a single binary output. That's all it can do. It cannot do more than that. And then it has some weight function inside, where it kind of decides if there's a certain threshold you can set and you can optimize it. That's kind of the magic. That's kind of what you train. So you train the weight, and if the inputs together kind of cross this threshold, this weight, then it becomes a 1, and otherwise it becomes a 0. Yeah. So we initialize with the weights. So this can be extended, as we will see, to, and it was extended also in '86 to multi-layer. So multiple neurons were used the first time to kind of form the first neural network layer. We still had 4 main disadvantages, so it was kind of interesting, but not really useful in that sense, because it couldn't train. It could only be used for supervised training, and it could only be used for labeled data. So that's one drawback with label solve. And also, if you use multiple layers, and this is why it kind of never really kicked off and became more. We'll see later that in 2006, this was exactly what was changed. That's kind of, if you use more layers and more than 2, the signal becomes too weak to actually become useful. And this is also what is called the vanishing gradient. So at some point, the gradient becomes so small that once you forward it over the network, it becomes too small to become useful, and it becomes basically 0. And also, it's very slow to train, and it really got stuck very easily in local optima. So that were some of the problems. But it was one of the first real neural networks, and they were used in this way. So you have one perceptron, and you basically stack them together in one layer, and then multiple layers, and you have a separate output layer. Yeah, so it could do quite some impressive things, but everything up to 2 layers. More than 2 layers, it couldn't really do. In that sense, it was kind of similar to SVM, which is also kind of can be understood as 2 layers. So in a sense, they were quite equal, except that SVM was much more efficient. You could do many more things. So yeah, the focus on the basically mathematics means that we have an input, we have a weight, and try to optimize that. We have also an error space, and we have a non-linearity function, which is a sigmoid or a time, and we map it into the same space. And here you can see it again. We have the inputs, we have the weights, that can all be separately optimized. With the bias, it can also be initiated different ways. And we have the activation function, where we try to optimize some cost function. We try to minimize the cost. We all get this. There's a lot of mathematics involved later, which we'll actually skip. But this is the base. If you understand this, then you know deep learning. So that's good news. So it's really simple. So this is the basic idea of deep learning. That if you kind of take this very non-optimal, non-working, quite shitty person prompts, but you do something really smart with them, and it was kind of found out in 2006, then you can get really quite amazing results, and you can go beyond the 2 layers, and you can train them actually also quite fast. Yeah, so there again, so again, all you need to know, input function, weights, there's some kind of activation function, and there's an output. And there's different, and there's many more than these nowadays, there's much better ones, but mostly sigmoid, for instance. And the idea is, yeah, with that it will always map it to a kind of space. So one thing which changed, which was in 1974, but actually only became known and popularized in '86 by Hinton, one of the godfathers of deep learning, is backpropagation. And backpropagation, or backprop, as it's called, is also pretty simple. It's like a generalization of the least squares. But we call it backprop instead. And Paul Werbos, the guy who finished his PhD on this, so he deserves all the credit. But this kind of made it possible to not only use linear weighting functions. So with this kind of mathematical trick, there's a mathematical trick somewhere involved here, optimizing gradients, it became kind of possible to use for some real non-linearities. It became also much more efficient to train neural networks. Yeah, so the idea is basically when you have errors, just do some way of calculating them back and use that, feeding it back through the network and kind of yeah, optimize the weights in that sense. And you do that layer-wise, so you do that layer by layer. Instead of using some kind of global error and you optimize them all at once, you do it in a more useful way. So basically how it works is when you start creating some output, you basically just you sum all the activations. So that's the 18 sum. You can use different functions for the activation function. And basically you just feed it through the network. But then once you're done with that, with one iteration, and you have the output known, and you know it because it's simplified data, so you know you calculate the error, and then you can derive gradients from the error. So kind of feeding it back step by step. And then you can basically, yeah, so you compute the gradient element-wise, and then you use the chain rule, basically very simply, where you just plug in, you know, your functions in this algorithm, and you use the chain rule to optimize the gradients. And then you can initialize it with something, because otherwise there's nothing to, you know, to optimize. If they're all zero, I mean, it doesn't really work because you don't get much of an output. So you have to do something to start from. So you basically initialize them. That's what used to be done, is that you initialize them very much random. And you have to do that in some way that the mean, for instance, is still around zero, or that there's some, you cannot have them like too far away from each other, because then it doesn't work.
The weights of the neural network.
Yeah, it's the weights.
You
set them to really small random variables. And they need to be extremely small. If they're too big, you will get what is called exploding gradients. So you kind of explode because, you know, the weight is big and you feed it through multiple networks, it becomes bigger and bigger and bigger, and it explodes. And, you know, kind of when you have your error space, you try to map your error space, it's kind of like it's way too far away from where it's supposed to be. To the optimum, you'll never be able to return. And if you have them too small, the opposite happens. It's kind of crawling forward, and at some point it becomes smaller and smaller and smaller until it's up to zero, and you're kind of done because you're to zero and it's vanished. And this is one of the things which kind of was found out, like how in a smart way can these ways be initialized. So yeah, the breakthrough in 2006. So what happened in 2006 when kind of deep learning was born? First of all, more data. So big data. Basically every 2 days, it's a known thing, you know, maybe not even so much true, but it's kind of interesting to think about it, that at least around every 2 days, there's as much data produced, and now it's even more until the beginning of times, until 2003. It's quote from the and also 90% of all data in the world right now is created in the past 2 years. And this will even iteratively get shorter and shorter and shorter. So that's a lot of data. So more data was available. Here we can also see that. Predictions for data. So more data also means that we could do more things with that if we were able to use it in a smart way. And especially there is more unstructured data. It's allowed for unsupervised learning or semi-supervised learning for NLP. There are some tricks you can do. Then, of course, more data also means you still need a kind of architecture or kind of the hardware which can make sense of this data. So you need to be at least powerful enough to train your network with all this data. And around 2006 or a bit before, but in 2006 around, at least the GPUs became cheap enough, at least for big universities, to also start buying them. And there were also enough insights to kind of how, on a more algorithmic level, how to kind of parallelize, in a kind of parallel optimized way, you can do your stochastic descent or something like this. So that's another way. And then there were some interesting, you don't know the difference between CPU and GPU, I guess. So we just have one cores and also actually faster memory. And then there were some new ideas on how we actually could train deep architectures. And the concept there is basically layer-wise, unsupervised feature learning. So it's again two things. Like one, what we said, how do you start the network? So how do you initialize the beginning your weights? And the second thing, well, once you do that, how also do you learn your features in the different ways? And there were actually different. There's actually 3 papers, but let's say there's another later paper also where somebody used autoencoders. But first of all, it was Hinton et al. Who kind of stacked restricted Boltzmann machines, and this was one kind of trick to use instead RDMs, which don't have connections in the same layer with each other, the neurons. It was a fast way to kind of train the network. And he also came up with some kind of this idea of greedy, layer-wise, unsupervised learning. So he came up with a new algorithm of kind of smartly training these kind of networks, very fast. And nowadays, actually, I mean, we can even train networks without these steps because it's much better understood, like how you can initiate the initiation calls or whatever, and also how you can kind of we understand non-linearities better, so there's better non-linearity functions than just a signal function. And there's all kinds of other tricks we can use as rectifiers or max out or more regularized methods as well. Dropout technique, maybe can also show later. Yeah, so then it basically took off. So onwards we go to deep learning, finally. Any things till now? Yes, go ahead. So there we have the godfathers of deep learning. So that's the guys who kind of came up with some of the ideas, which at least ticked it off. Hinton, which was immediately hijacked by Google. Benjo, who still stuck around and is still actually at the University of Montreal, but also actually got his chair now sponsored by Ubisoft, I believe, by a game company. And of course, Raccoon, who also, I think in 2013, was fired by Facebook. And that's actually where most of the interesting NLP research nowadays in deep learning is happening, where quite a lot of big names, all of them actually come from there, and Western, I think, also, and others. They all kind of started to work with the kind of Facebook right now. There's a lot of interesting things coming from Facebook research. So why do we want to go deep? And what does deep mean? Well, we know what shallow networks are. Shallow networks are networks which are not deep, okay? But also they cannot really represent very complex functions. So the more shallow a network, the faster it is to train, but also the less neurons you might have, let's say, and the less layers. And it's kind of found out that instead of having a very wide network, it's actually much more efficient and much better to have smaller but more layers. Because more layers can represent actually much more complex functions in a much more efficient way. Yeah. So you see that, so they're kind of hierarchical. It's not in a way only that you can have a lot of layers stacked in neural networks, but it's also that different layers can learn different kind of representation of your data in a hierarchical fashion, where the most simple interpretations of your data are like the lowest layer, and then every higher layer, because the weights are fed towards the network and also the backdrop does it layer-wise, is kind of optimized in a layer-wise fashion. You get kind of like layer-wise representations as well. There's no global representation. Every layer has its own set of representations, and the neurons in a layer, they kind of work together, so they can, every neuron can become highly specialized in a certain representation of your data, but at a certain abstraction. So they're all at the kind of same abstraction level. So every layer adds another level of abstraction. So the more layers you have, the more abstraction you have. And we'll see, computer vision is much easier to kind of explain. For NLP, this really doesn't mean so much as such, because words are much harder to kind of, when you have, let's say you have a bag of words and you have multiple words together, and another abstraction might be, characters. There's no sense that different, similar characters have any kind of similar meaning, because words are kind of another abstraction by itself of our conceptions of how we talk, how we interact of the world. So words are already kind of abstraction in that sense. Yeah. Then we can share also, so kind of strengths in different layers can be shared, as well. So kind of statistical sharing of statistical strength, as it's called. And then the good thing, we can build distributed representation. So we can kind of map different parts of the layers in different ways, because we already use, the neurons in the same layer are not connected to each other. So you can, for every neuron, and by itself, and a separate machine or a separate GPU, it doesn't really matter. So in that sense, it lends itself extremely well for full parallelization. And that makes it possible to have clusters of like thousands of GPUs work as the kind of same neural network. Best of all, no more handcrafted features. So we don't really have to annotate much anymore. At least that's the ideal. And especially we can kind of exploit all these, tons and exabytes of data which are out there on the web and which are unstructured. If we can find a way to use those, and this is what has been done over in recent years, we can get a really, really deep understanding of the world and of language or whatever. And G also said, I've worked all my life in machine learning and I've never seen one algorithm that's going to be backprop, knock over, benchmark like deep learning. And this guy knows it. So again, yeah, deep learning is brain inspired. So just as the brain, I will not presume to have any deep knowledge about the brain. That's not my thing. I'm more in the field of pragmatics, like whatever works is good enough for me. But basically, we do know that from the first layer, let's say it's the input layer, your retina, if you look at like how your brain interprets what you see. It's kind of where you get your input the first, and it's the fastest. And then the further away you go, so the further away, the more milliseconds it takes, for the inputs to arrive there, the more complex the abstractions are also. So earlier kind of layers in your brain have simpler concepts, which are then iteratively used to construct the more complex concepts. So yeah, so the different approaches to this. Where I work at Feeda, I have a colleague, Jorge, who's like a brainiac, so he comes from the kind of brain part, so he knows what brains, and I don't. But that's kind of how you can see a lot of times when there are discussions within the field of deep learning, a lot of times it kind of comes from positioning where do these kind of things come from. And do you compare, do you understand deep learning as an actual representation of the brain, which will be really close to that, and the KTH system, computational biology. I think Paul Hermans, for instance, gave a presentation once at Spotify, at the machine learning lab. And then there's also a computer vision lab, where they take much more a pragmatic approach to basically, they just want to do computer vision. The brain part is nice, and you have to understand some of it, but it's not the main part. So yeah, again, you have the input in your retina, let's say the pixels, and then you have different kinds of detectors, where you first get the edges, which are kind of combined together to understand primitive shapes, and then you get all kinds of higher level abstractions. And one of the ideas, and there's a lot of people who have written papers on this, is the idea that deep learning allows you to actually, because it's modeled on the brain and the way we think, in theory, when we say it's maybe around 20 layers, let's say in your brain, it's a lot, or probably much more. But with up to a certain amount of layers, we theoretically should be able to represent anything. That's the idea, because of this. And there's a lot of theories behind it. Yeah, we'll see how that works. Yeah, so here we see it again. We have the pixels. In the next layer, we can combine pixels together to form kind of edges. So this apparently, when you start optimizing, it's the most meaningful way to understand vision. The next layer, we start combining the edges together, and you start representing parts, shapes, or parts of faces, and these things together, and you start getting actual objects or faces. So this is generally what you can also quite neatly actually visualize what is being constructed in the neuron. So you can actually see this. So these are actually not real, maybe, but kind of real things in reality. So the idea is that it's hierarchical, from low to higher. Yeah, it's easy to monitor what it's doing. And in that way, it's also what is called multitask learning or transfer learning. The idea is that when you have one network or one representation, you can actually use the same kind of network or the same kind of trained network, which you might be training for weeks or whatever, on different tasks. Because what it does when you feed it into it, especially when you do pure unsupervised training years ago, what it actually does in these layers, it starts representing. So representation, when you start representing your data, and the idea is that it really comes up with good features to represent your data, which might then be very useful for other kinds of tasks. So you can train, you have one data set, let's say ImageNet, a very good computer vision data set, you start training on that, and you have also on top of the network, you will see you can have some kind of classifier where you have some way of, you have to backcover that error, so you have to know some kind of ground truth is. But once that's trained, you can cut off that layer, which is the only layer which is specific to that data set that chunks. And you just can put on different kinds of classifier for a whole different task. And you can get really, really, really good results. And what is also done in natural language processing, for instance, that when you have a lot of labeled data, for instance, for one task, this can be used to start training a network and then actually use it for a completely different task. This is one way how a lot of the state-of-the-art new already, for instance, on named entity recognition really work. By training it on huge data sets of language and then trying with something else. Yeah, and we could plug in, again, you can plug in whatever. This is audio, and you can plug in NLP as well. So here we have unsupervised multitask learning. So again, you can have different tasks. So here we have your actual feature representations. Let's say you have many more layers. Here you have actually your different classifiers, but on the same network and the same features, on the same data maybe even, and you can have different tasks. So again, the whole big hallelujah idea here is that you have one huge network that can do that. That's easy. So that's a classic deep architecture. We have the inputs, we have different layers. Layers are not connected to each other. they're directional, so you put it always to the next layer, and then you have an output classifier. But then there's also modern ways where you can see that actually instead of having one direction, you can have it multi-directional, and in some ways even sometimes combined. And I will not go into that because it will become very difficult.
What does it mean to have one direction or two directions?
I mean, the difficulty here becomes that when you propagate your gradients, you can really efficient when you propagate like your input through the network and propagate it with the gradient. When let's say this, let's go one back. When you say, for instance, let's say this one is connected to multiple neurons, and normally one is connected to many of them. It's not just two. The point is that you can the gradient that's called here can be used in all these different ones because they're layer-wise, but only if they're in one direction. If they're in two direction, they can shift back and forth, and you don't really know what happens. So there's no global. It's like traffic on a road. When everybody keeps moving in one direction, there's a kind of continuity. But when there's also people moving back and forth, it becomes kind of chaos. So there's no general logic anymore. The kind of general logic is lost. So you need some higher level function to kind of have still some logical idea of doing that. And especially there is another type of network that's used a lot in NLP, recurrent neural networks, where you basically allow neurons or layers to connect even to itself. And this means that layers of neurons, they can hold information over time. And this is very interesting, for instance, for audio, where you have where you keep the gradient of, for instance, the last 20 input signals. It can keep, you sum it all the time together, so it can keep the same kind of input for a big time window. And you can kind of use this whole input as a kind of way, or for video instead of images, that's what you have to use. You step them all together, you can start getting these kind of features. And you can see it kind of as what is also called unrolling the weights. It's a bit technical right now, but basically means that let's say you have one input, you kind of hold all the gradients kind of in the memory, and you have, instead of having one neuron, the trick is that you kind of copy, you make a clone of the neuron. You do your populations and you kind of then store it back.
So can you say, like, for example, that when we have a like bidirectional, means that the property of the weights of the decision of the learning is like kind of dependent of the same inputs. Like it's like when you do name entity recognition and you have a Markovian, then there you have a dependency of like each token is dependent of information of the neighboring one. So
it's
then
kind
you
of
have
like
to
you have
get
this
back
like context
and keep,
window instead of having just
it's a context window.
or when you have back of words, where let's say you take only the words, but instead you can also have a continuous back of word representation, right, where you actually keep track of the word. So that's kind of what you can do when you make them bidirectional kind of link to each other. But it's, I mean, you need it's kind of based on a hidden Markov model. That's more. So yeah, deep learning. Why again? But if you're interested in recurrent, we'll see later. I will not talk tomorrow specifically on recurrent neural networks. For those who don't know more. For anyone, it's at. I will tell later more about it, but it's basically for whoever wants to go by as well. Because they're way too complicated. It's a completely different way, to think about these things. So deep learning, why again? So there's some other state-of-the-arts. Language modeling, language recognition, image recognition, sentiment classification, and all of these, or most of these at least, are already beaten again. But these were, at least then, one of the first times at least that deep learning was used as an approach to beat these benchmarks. And then if we see deep learning for NLP, this is all kinds of tasks. Just a big list of think it's the last few years, maybe 2 years or something, different NLP different tasks for deep learning already were tested on and benchmarked. So it's a lot of them. So basically, it means that there is that it's quite a widely used approach nowadays for natural language processing with varying results. Still have a few minutes, I think, or yeah, because I'm basically done with my talk. But I can say one more thing about that's really short about deep learning as such. There's some interesting things you can do with deep learning network where you use unsupervised learning just to represent the data. And you get like with these different feature hierarchies. That means that you can represent really complex ways and different ways for the data. You get a really good representation of the data. And this can then be used afterwards. So this is kind of initialization of your supervised algorithm, let's say. So then you can use that afterwards to then plug into any kind of, let's say, some soft or max out or max out classifier or whatever, any kind of supervised algorithm to then do NLP tasks. And this is how most of these, except maybe this, yes, no, most of these actually, except the ImageNet one, but most of these actually have been run just through that. Training network, pure unsupervised data, you have no idea what the ground truth is, but a lot of data. So you get a really good generalistic model of your huge language or computer vision data. So really, really low. And then as much layers, let's say, if you can do, so you get like not just really general, but you have a lot of different layers of different abstraction levels, which are all by itself have a general idea of the data. So it means that you have both general, but also specific. So every layer is specific. So you want to actually have a smart combination of generalistic knowledge, but also specialized knowledge. If you do this in a smart way, that can be used then to train supervised tasks. So that's it. So for the break, here on GitHub, so people are linking up on their laptops. I put up a Git repository. There's 3 IPython notebook files for people who think it's fun, but I will just go through them, so you don't really have to, but you can. Yeah, and basically we'll be training a multi-layer person from network, so it was one of the first network trained, so we'll use both of them on a very simple data set, so we'll use the NIST, handwritten text data set. But it will perform still quite okay. We can train it even quite fast. And we'll do the same thing with a convolutional neural network, which is very different. I'll explain also more how that works. This is the most popular network or deep architecture used for computer vision. Yeah. Time.
I think it's good to keep the page on so that people, in case they want to download. And yeah, we are running a bit behind the schedule, but I think we can squeeze the time from end of the time, so it's fine. So let's sit together like at 5 minutes to 8, so like 15 minutes break. And yeah, we will have the next session.
Yeah.
What happens if we just pause it?
Yeah, you can only stop it. I think you cannot pause it.
Okay, so then leave it on.
Nice.
Okay.
Thank you.
So you created a new
Control over data. Compromises a lot. That's why. And that is what you are. I already made someone. Yeah, sorry. That's basically he basically is how we interact.
Focus on Twitter. They have to stay. What they did the last one.
I think you should get back to the presentation. Guys. Where's the then I can move this a bit. Yeah, you're there. Okay. So let's start the second part. Yeah, I just want to apologize that I noticed that I didn't put the company number and my number in the invite of this meetup. So sorry, some people got left out. So yeah, we are learning how to organize this event. Next time will be better, I promise.
Yes. Do we have some people who are joining in?
Is there an internet password for the guest?
Yeah, there's no guests.
Yeah, that would be also the next thing to fix.
I could possibly share my network with a few people on this device.
I can try it. Yes.
There's a small data set you have to download.
Just
Amnist. They're not very big, but it's good to know for the people who are getting their phone started.
So everybody needs to speak. My network.
Okay, so
So for those who have cloned the repository,
sorry, Roelof, before you start again, if I'm sharing my connection, so it's just the iPhone and A123. If you write it somewhere that people can see. It's A12345 and then ABC. Very secure. And it was not on amount, so.
Can you give the URL again?
Yeah.
Where
I'll give both.
you pick up the
Yeah, it's graph 50. There's only one repository.
Do you have any tips for how to just install piano on a Mac? Because
Yeah, I have a
couldn't
Mac here.
get it to work. I could on a Linux, but not on a Mac.
So here there is starting piano. So basically, this should just already work. Just pick install piano. But maybe there's some dependencies you need.
Is it included in Python too? Perhaps like
Yeah.
trying
Basically, why I learned is basically uses piano in the back. So if I want to learn, you also have piano. I mean, there's more complicated ways to kind of compile piano if you want to have a GPU support, kind of fast optimized way, but just the standard install of piano, which I'm actually using now also. So it's just quick install piano.
Installing piano doesn't work if you're using Python 3.
No.
Basically.
No, you have to use a separate branch.
I have a separate adversary that you can use for actually compiling Python 3.
Yes,
I don't
please.
know, but
What happened for me was that it installed like from Pip, but then when I imported it in Python, I got like a runtime error that related to Clang.
There's a compiler, so you need to maybe do also pip, or not pip install, but the brew install GCC, or like some of the newer C compilers. It can be like the Clang compiler. It's the standard C compiler on OS X. It's not simple, it can do lots of sometimes Clang is a bit are we ready to go? So let's go ahead. So let's just run. I mean, there's this pre-workshop thing, which is hopefully it should kind of give some examples of installing Python and IPython and Java. So for those who have done that, have cloned the repository. So make sure also to git clone with recursive, because there's a library I'm actually using, which is the Deep Learning.net tutorial. Everybody will everything you want to know on deep learning, just go to deeplearning.net. And there's Lisa Lab, which is one of the labs in deep learning. They have a quite good collection of code. So basically here, deep learning tutorials code. So that's a sub module. It's included in my repository. And if you don't do that, also no problem. Then you just get some module update in recursive. I can do it also here if people want. So you just have to go git clone this one, which you can also just find in the repository. So if you go here, you can see here also the nice link. So if you need git clone, that's recursive, and this URL here. And it's also and then some of the stuff I'm actually using, and basing it on some existing compute fast code. But let's start. You can run it all by yourself also later. But that's for the people who are. So this is basically just I'm importing Piano here. So basically I'm just importing Piano and Matplotlib for the figures. And then I'm inserting the extra code I'm using, because I didn't really want to, more stuff in there. So here I have one of the functions, which you don't bother much, but basically I just use the function load data to load this data set. The good thing of this function I'm using from here, basically it also helps you download the data set if you don't have it. So you just work on it, so load it. And I've written a bit more explanation of Theano in shared variables. Theano is basically like a symbolic library of program language which you can use to do deep learning quite well. And there's a lot of other libraries based on Theano, like DY learning stuff. And it kind of has this thing called shared variables, which means that you can actually kind of create the variables, but they're not really there yet. But it means you can really efficiently already compile the functions, so they become behind the scenes, they become compiled in C code, so they're very efficient. So you can, make your gradient descent function and already plug in all your stuff and compile it to C without actually giving the data there yet. So you can have your whole skeleton of your deep neural network ready, and it's already compiled into C code behind the scenes. So the only thing that's missing is just if you put some data. But yeah, I think I actually have myself an older version than the repository from that. So basically what you can see, we've loaded it. We have 50,000 images. And this is some of the images. So it's basically just a collection of like handwritten images. We're going to basically train neural network. And one of the things which you do with neural networks, one of the really important things is how you kind of deal with your data. So how do you normalize your data? How do you try always to make your data set as big as possible? So there's all the kind of tricks you can do with data, rotating the images and mirroring them, sampling them, making different kind of parts of it. So you get all these kind of different representations of your data. So it becomes more generalistic.
It's the mixed data set, is it the vectors?
Yeah, this is just, that's what it is. So it's one of the oldest data sets.
It's just digital numbers.
Just digital.
Only digits. Yeah, it's only digits. And it's actually taken from a big data set of actual people handwriting. That's actual handwriting. It's not a very difficult data set, but difficult enough to use. So now basically we just normalize it. And how we normalize it is, it looks weird, but what we basically do is that we just kind of make it more according to the mean. So we kind of take the mean of the, how bright the images are and whatever, we just make it more kind of even.
You subtract the mean from every image, right?
Yeah, exactly. So kind of even out the images, kind of make them more apart from each other. And then we just make the different training sets. So again, now we start with the real stuff. So we have the data. We have loaded the data also in 3 variables. We have a training data set, we have a valid data set, we have a test data set. So that's basically what we've loaded all these images in. And now we basically start creating our logistical regression model where we have the weights W and the bias B, if you still remember. Should have put some more pictures here. But that's basically it. Then we have the data, which was mapped to X, and we have the output, which can be true or false, which will map to Y. So Y are the class labels. And we start predicting with a certain probability the Y, like what is the image. And we use the train data as the ground truth, and then we can test it. So here, basically, it's not really important, but we basically just declare variables. This is some internal Theano stuff. But basically, here we say, okay, we make our log likelihood on our predictions. So here we can kind of have our prediction softmax layer. So that's kind of the layer we use to make predictions. So then here we want to convert that into the class probabilities. So we map what gets output in the logistical regression, we actually want to map to the different classes. So we have, all the digits, 10 classes. So that's here. And then also we want to be able to compute the classification error. And here we basically just take the cost function. And the cost function is the negative log likelihood. It's basically just a probability. So that's that. And also, we basically I will not bother like writing the gradient function. Piano has a very nice function for that, t.grad, and you're done. So with that we can compute the gradients. So basically the only thing we have to fill into the gradient function for Piano to understand what we want to do is basically the cost function. And here also the weight, the bias. So we have here the gradient function for the weights, and we have the gradient function for the biases. Then for now, we set the learning rate just to 0.1. We don't do anything more with that, but there's different ways you can do to kind of start lessening the learning rate more and more, the closer you become towards the local optimum. And then we create the update rule, which is again here, which is just the rate minus the learning rate times the computed weight gradient, and the same here for the bias. So this is basically just already enough to create a function to compute some values. And then we have a function we also take from Piano. We create our own train and validate function, where we make use of our update and our error function, which we just create our updates and also our error. So this is basically just a way of mapping symbolical functions. So don't bother much understanding. Basically, you can just read for this. We just run the function error, and here we run the function updates. So let's start with the real stuff. Here we have some variables where we just keep track of the actual values. And we basically just want to do it 10 times. And every second time we also put out what is the training error and the validation error. So here we have the loss function. We basically just train on the data. So basically we say this is the input, and this is the output. And here we basically save our functions. So there we go, training. And we're done. 5 seconds, and we have an error rate of 0.13. Not really bad, not really good either, but for such a small, just simple logistic regression. So we're not doing even like neural networks just yet, but it's like part 1 of the 2 parts we need to create a neural network. So this is the logistic regression function. And we can see over time what is, how does our cost function, error function get us. So we can optimize this. We can have a load black box, but I will not do that now. But basically what we do here, don't bother understanding. The only thing I do is that I, instead of recalculating the shared value all the time, I save it. Let's put it to 100. So this one should be much faster. It's just a kind of smart trick of keeping track. So we see it's much faster than the previous one. Go to 100 very fast. So just 100 iterations in 30 seconds. So you can imagine running this for a day. You get a pretty good result. And we're now at 8.9% error rate. And here we were at 14. So a bit better, still not really amazing. And this is how it looks like. We can do the same, where we, instead of validating it for every iteration, we do it for every certain amount of iterations. So here we, for instance, do it every 20 times. So it's batch training. And it does something really, 9, okay. Still quite okay. So it's another way, again, faster. It means that you don't have to evaluate your general output with your validation function every iteration, so it's faster. But instead, you run it 20 times, or mostly you do what's called mini batches. So maybe you run it 100 or 200 iterations, and after that, you kind of calculate the error only. So you only do it once, and you take the average. And then only then, so you still want to have all the errors saved to sum them. But after this kind of first batch, you do it iteratively, that's when you update, or kind of validate like what you want to do with the gradients or the weights. So you kind of get this more, you draw it out here. So it becomes more like this, because that's when you update the weights. Then another thing we can do, where we see here, where we have here, that's a bit different. So we still have the same learning rate, but we all the time make it less. So every iteration it becomes 0.05 less. So it becomes 0.5% less every iteration. So we slowly start making the rate less. If we map the error space, it just means that you take smaller and smaller steps within the same error space, so you don't overshoot at some point. So this is just that when we make the neural network, you kind of understand what we'll be using and can use, and also if you want to yourself play around, you at least have the different functions or things to do. So now we have that. We can finally start with the real layers. And we use a predefined logistic regression class. So here we import it. And this is again to recap. We have our input, we have the inner layer, and we have the output. The inner layer is just the bias and just the weight. So these ones have all the weights. And there's a general bias function here.
Does each node has a different bias?
Yeah, every has its own bias. Yeah.
They're not necessarily the same.
No, not exactly. They're not. That means that you let different nodes specialize in different things. But the kind of input, you see that they're all connected to the same. This is kind of restricted both-on machine approach, where every node connects to all the others, but they don't connect to each other. So that means that they have the ability to each specialize in their own thing, but still with the same data. But they can each specialize in their own weights, so their own importance they assign to certain parts of the data, and also their own kind of bias element. Lets it have a certain view of that data as well. So it can kind of shift it in a certain direction. And you can imagine that if you start doing that with multiple layers, it becomes exponentially more possible to have differences in that way, because you start reusing all these things all the time. So here we have our nonlinearity function, our sigma function. I have to go a bit fast through it now, so we're not out of time, but on the deeplearning.net website, there is a really quite long so nothing happens yet. So now, doesn't look really exciting yet, but we have a logistical regression and we also have a hidden layer. So let's create our multi-layer perceptron. So what we'll do, we have our hidden layer here, and we have our logistical regression layer, and we can give it, as argument, we can give it a certain amount of inputs. We have our own observation function. We have the log likelihood, which is basically the probability function. And here, a lot of text. But yeah, basically it just says that we have a lot of hyper parameters here, which we let it train by itself. So there's a lot of different parameters we can do and we can shift around in the network, but instead of assigning that, so we have the weight, we have the biases, and there's other kind of arguments you can use in inner layers. But instead of having this as a kind of standard thing, we let, of course, the network itself train and in a way decide what are the best kind of parameters there. So what we do, we have the number of perceptrons or neurons we have in our hidden layer. We have a classifier. We decide the input, and we also decide how much there is in the output. So what we do here, we go back to the picture. We have 100 of these guys, and we have 10 of these guys, of girls. So it means that here, everyone will be specified for one class, so one out of the 10 digits. And here we have around 100 neurons who will be playing with the data, representing the data in different ways. So the function is compiled, as it's called for Theana. It's a bit different way of working, but the function is there, so now we can run it. So we want to also see how long it takes, but we want to run it for 20 seconds. So let's see what happens. I also set the mini batches to 2500. So we see it's already much, much better. We now have an error of 3.7. And we also see that it's very, very fast. It doesn't really take long to train these networks, even if we start adding more layers. So what's happening? This is part. So we have around, how did we visualize it? Oh, basically this is all of them. So it's that. Representing, we can actually visualize. It's a nice thing of computer vision stuff. You can actually see quite easily what is in the layer. So we haven't trained it very long, but we can
weights after the activation. Yeah, but they are in turn components of all the weights from the first.
Exactly.
So it's not just really noise. It's some kind of more smart representation of everything.
Yeah, I mean that's why it also doesn't make sense. Mostly, these kind of layers. I mean, not for the human eye. I mean, you wouldn't see anything here. For computers, this is highly useful. For us, not so much. And this is more the features. This actually do make more sense.
But if you group them, the samples by just first all the zeros and all the ones, then I guess it would make sense to us too.
Yeah, that's, yeah. I mean, then you still have to know what it is. So yeah, let's go all the way through this. Basically, it's just a function to have more layers. So we added another layer now. We want to see if that kind of influences. Yeah.
Is it possible to put some kind of prior knowledge into these deep nets? I mean, for example, the digits, the handwritten digits, we all here know how to interpret that. So is it possible in a way to put a prior on these hidden layers, what they should try to identify?
Yeah, I mean, for sure, you can do that. There's people, for instance, doing optimize some of these hyperparameters, as they're called. So in different ways. But mostly what you do is when you want prior knowledge, you kind of use something in front of this layer. So you have some kind of way of like playing around with the data in a way to kind of make it more understandable. And then it's up to the hidden layers to kind of use that in some way. That's kind of normal, that's most of that. Yeah.
I think a simple explanation to what you just said would be like a mask, right? So like if you say, like for identifying a one, you just make a mask that is just a vertical line, and you mask the pixels that are outside of that, and only so all the handwritten ones that fit into that mask will be so much cleaner, and then you train with that. Is that what you meant, right? Putting something before putting it into the neural network, like pre-processing.
I mean,
the data.
that's definitely possible. It's only kind of beats the idea of not having to bother with this kind of stuff anymore. But
No, to answer his question.
Yeah, no, sure. Yeah, that's certainly possible. It's
So
not done much.
The noise. When you know for sure that something is noise, you take it out before feeding it into the neural network.
Well, actually, the opposite is sometimes true. There is actually a way of when, for instance, your network overfits, or you want to make it more generalistic, there is actually a way how in a kind of smart way feeding noise into the network to make it more generalistic. Or there's another thing, for instance, it's called dropout, where you kind of turn off half of your neurons. So kind of you allow half of the neurons, every iteration, different random ones, to kind of represent the data in some way. So instead that they're not connected. So they become very, very specialized. But by doing this, you kind of allow them over different kinds of data about true time to become a bit more complementary to each other and get a kind of better representation of your data. And there's a lot of more of these kind of algorithms which came out, kind of smart ways of tuning or playing around with mostly hidden layers. And again, we don't see so much yet. And it also has to do with we visualize the hidden layers. There are different kinds of architectures, like a convolutional neural network. I'm sure we have time for that, but if you like nice visualizations, they are much better fit for making nicer rounds than these ones, because they actually work better. That's how it looks. That's the plan. Do you want to go on to now?
Well, I think
There's another network I will just go through fast, just so we can see. So it's very similar code in many ways, but a bit different. So what we do now is called a LNet, convolutional neural network. So one of the earliest ones, this is actually one of the networks which was actually doing quite well before the 2006 books. It was actually, I don't know how much, but a quite big part of all the checks in the US were actually scanned through this network. You can recognize like OCR. Yeah. So convolution, but we have to kind of return shortly. So this is a convolutional neural network. And especially it has become extremely popular in 2012 when it was used to win the first time the ImageNet competition. And it's kind of split in two, which makes it hard to understand because at that time GPU cards were not like, didn't have enough memory to represent the whole network, so it had to be split up over two GPUs. And Krzyzewski was then just PhD student who made it in his bedroom, he was running it or something. And he was the one who kind of won the ImageNet competition. So basically, the idea nine. So we make the images smaller, just to be able to train faster. And it's one because it's grayscale. And then this 9 by 9, we convolute into a smaller representation of 5 by 5. That's understandable. So we kind of represent the 9 by 9 image into a 5 by 5 more convoluted image. And then we feed it into a sigmoid layer. This is kind of just a way to make it more non-linear. It's a non-linearity function. So here we define it. That size 100, learning rate 1. This is my own hack, but you don't have to run it. It just means that it takes only 1/10 of the data set. So, first layer, we're basically reshape the input to 9. We have a convolutional layer. We have a second convolutional layer we also set. So we make it 5 by 5. So that means that we take a 2 by 2 region and it becomes 1 all the time. And then we have our fully connected sigmoid layer, which we feed into our logistical regression. And then we train it basically exactly the same way. So the general training code as such is almost the same as before. It's only some of the layers which we change in the way how our input gets kind of routed through the layers. And we do something different with the data. So it starts very high. Mostly because so it also gets down very fast. But it's mostly because the convolutional neural network needs much more data to be able to work quite well. And if it's there, then it works really well. So I limited the data now to like 1/10 of the original size. This makes it actually already quite small to be able to get anything meaningful. But still, it's optimizing it. So it will do something, but I don't think it will be able to get much. Still getting a bit better. Maybe you can get it around 10 maximum or something. If you do like this, you won't be able to optimize it very much. So again, if you want to have really nice visualizations, this good score just don't limit the data set and run it for a longer time. Because as an idea, this is similar. So here we have basically first layer. So this is already the first features. And next layer, as we can see, it becomes more noise for human eyes, and then so it becomes more and more noisy for human eyes, but it's somehow becomes more and more understandable, at least for the computer, because what the computer only wants to do is to find some logic in it. And the brain is able to do so. And then check the final error in a separate test set, which is actually better. This is better. So it means that it's more generalistic. So it has actually a higher error on the training set, but it does so because it convolutes. And through doing that, you actually make a more generalistic model. So these are convolutional neural networks. They kind of they're much more generalistic in their approach and get much better results in that way. So that's it. Then I go back to my last few slides in the presentation and a bit of time. I can just show. So what's going on right now with current developments in deep learning? I didn't talk about recurrent neural network or recursive neural networks. It's two quite interesting approaches used a lot, especially for language based on the market field. It's quite interesting, and also especially long short-term memory, which is mostly plugged into this kind of recurrent neural networks, a specialized form of recurrent neural networks. So recurrent neural networks, just like in the market fields or in the market layers, kind of can link up to themselves and to others and back as well, and through that they can kind of keep track of previous gradients or previous data.
Is that what DeepMind do? Because they're doing
no.
something like deep learning with networks, right?
Yeah, exactly. They use, I mean, they're really big in this.
Yeah.
And they're specifically also very big in a kind of third way of reinforcement learning. So what DeepMind kind of has been doing, what I don't know, was like bought by 500 million pounds, I think, even in the end. It's not never completely like declassified how much they were bought, but it's a British company. It still exists. It's now part of Google DeepMind. They were kind of bought by Google after they had a quite interesting paper on combining reinforcement learning with deep learning. It was called playing Atari games. So they managed to kind of play Atari games. So just pure from the input of the screen, and only saying what you have to optimize is the score. That's it. Do whatever you want. And just after enough iterations, they became like superhuman in playing like Breakout or whatever. It's like really quite cool. But they did this through reinforcement learning. So they did this in a different way when you have an agent that kind of learns things, and then maybe and of course which is then also useful for all kinds of other things. But they're quite secretive. So nobody really knows what else. I mean, there's other smart people working on. Yeah, and again, some problems with deep learning. So again, it's not easy when we talk about, okay, how can you, use manual supervision inside these networks, or what they do. There's some interesting work actually on knowledge domains and plugging that into, and then there's some quite it's kind of working, but it's not so easy. And also this kind of bias space, as we visualize it doesn't necessarily have to mean much for real. For instance, here, it's one paper. Deep neural network. It's kind of nice, cannot be recognized, and you know exactly how to do it. Maybe wearing some of these random lights, so it's not possible to see over your face, and your face still looks the same, but for those who also want to play, there's some more. That's right. So thanks for listening. And for those who can't get enough, tomorrow I have a talk on visual semantic embeddings. It's more advanced, and it's specifically focused more on language, the language part. So basically, it's about if you have word embeddings, which I can show some examples now very fast. Also, at home with my research is mostly about how can you combine. Let's say you have a deep neural network and you train it in a smart way that you can combine images with text, and you have some way of doing some smart tricks with it to kind of learn what the image is about. So if you have a description of the image, you can map certain parts of this language to certain parts of these images, and you get a really kind of generalistic model of being able to transcribe images. So pure from image data, you're able to describe it textually, grammatically correct. And the other way around. So you can also type in queries and you can find the actual matching images. And it basically allows that when you now go for YouTube or something, you get really weird results, when you have your recommendations, you have some horror clip you're watching, but then you also get on the side My Little Pony, because it's very much dependent on the descriptive part, which people describe as texture, pure texture. So that makes it really hard. I mean, you need really a lot of textual description to be able to represent it. But what if you don't have to do it? You can actually understand just pure from the image or from the video, you can describe it by text and all the way around. And this is mostly done through the language part, which is called distributed semantics. People here are also working on. So the one of the early work. And it basically means that when you have words completely unsupervised, and if you want to know more, then come tomorrow. This will not really explain, but basically what happens is that similar words end up close together. So this is just a zoom in of the big word cloud we saw before. And this can then be used. This is pure unsupervised, but you do a smart way when you have your data. If you kind of make it semi-supervised, so an unsupervised, you still are some way of training it. If you say what is better than something else, and then you can get this kind of results. But when you use this, then you can plug supervised learning algorithms also on top of that. And then you get similarities. You get multiple words where you can have, for instance, multiple responding twice, and you can do disambiguation, so you don't have the same word. So you have multiple meanings of your word in different places, and you can quite easily disambiguate. You have what people know maybe word to vec, which was really the rule. You have kind of linguistic regularities where you say, okay, take the vector, or wherever what represented is two-dimensional. You saw in the picture, but it's actually really high dimensional. It's impossible to visualize. It's maybe 200, 1,000, 2,000 dimensions. So it's continuous vectors. So take the vector of king, subtract the vector of man, add the vector of woman, and which vector is the most similar to the output is then queen. So you can kind of automatically, unsupervised, it starts to kind of ingrain all kinds of knowledge as well about that which are similar, not just similar as one-to-one, but also which relations are similar. You can take the vector of take the vector of Germany, subtract the vector of Berlin, add the vector of Italy. Of course, you get wrong. This is just some more examples of that. So that came out early in 2013. Some more stuff. How when you have two different workspaces, how can you align them in a way when you have enough data? You have some time for machine translation, and this was actually quite a breakthrough in machine translation through this. So Google Translate, for instance, is run for multiple multilingual corpora as well as monolingual, and kind of combine them together for translation. There we have the recursive model, where I will not tell, but basically you can subscribe not just semantic knowledge, which we had before, meaning of words and how they map together, but also syntactic knowledge, so the structure of words and the structure of sentences. What is the way that we push words together? If something is a verb or something is like grammar or whatever, how can we bring this kind of knowledge in the neural network as well to then use for all kinds of tasks? And this is just used for sentiment. So this film doesn't care about cleverness, weight, or any kind of that anymore. So basically, what this model can see to a tree structure, this is all very positive. But just the fact that here it's negative and that this is on a higher level than these ones means that this is actually a negation of what comes behind. So the opposite is true. So it's basically negative sentiment, etc. And then some new one. And the word to vec clone, where it basically said, wow, we're doing much better. And this is another warning when people, maybe more for academics, when you publish stuff, don't be too excited about your results. 11% more accurate, and then someone else takes a better look at your paper and finds out, well, quite logically, if you compare different data with each other with different arguments, and you train the one on a much higher dimension than the other one, and you get better results, you have to kind of compare the models in a more even way, and then you kind of have very similar things. And the last one, when you have back of words, and you also want to make a word space. In a similar way, when you want syntactic structure, not just in a tree-based approach, but in a what's called a dependency tree. So you want to say that scientists discover star, and you have the dependency structure there. How you embed this in the same word space as you would do with normal sentences. Then based on what you get, you have much more functional similarity than it can. But it's different kinds of similarities you also can get in word spaces. So that's it.
It was a little bit over time, but I was enjoying it, so I didn't interrupt you. We were supposed to have the mingling, but I think we can use the time for questions, like a couple of questions if anyone has any question. Question? No? Well, I have one. So now we had the first session of deep learning. So I was wondering, like, you know, to give just a feedback that what would you like further to hear about deep learning, or if you can contribute further for the deep learning, any input? Because if I leave it for later, you won't probably write me anything. So just you know, if you feel, because we you know, we can invite people from, for instance, GRAP, or we can the Computer Vision Research Center in KTH. They have different applications, or if I manage to invite Richard, still I haven't managed, but then we can hear about sentiment, or even me and Bashka can present it. Or I don't know, I mean, I'd like to know what would you like to hear more, and what would be interesting, or yeah.
Something that I really liked about today was that there was this tutorial part where we went through code and explained how things work and showed graphs and results and all that. So I would love to see that again. So that's the students' perspective.
And we just saw these word to vec things, and I've been working a lot with them recently because there's a nice Python library, Jensen, so I could show what I know about it. So if somebody's into it, maybe it's David.
Just I don't see your name.
Oh, Henrik.
Henrik. Okay. Because then I can catch you, you know, in the place and ask you. Yeah, that would be nice.
Maybe it would also be nice to do some collaborative in some way. I know there's people from Copy Guide.
Yeah, yeah, exactly. I was about to
semantics.
say
I'm doing distributed semantics. You start doing this.
And because the Jensen assumption is not really straightforward. Yeah, we talked about it.
Yeah,
it's
I
pretty new, right? Yeah, it's very new. Or like 3 months, 2 months.
There's also RNNLM, which just released. It's kind of a recurrent neural network language modeling toolkit.
Yeah, there was
A lot of this. It's actually
So-
one, yeah.
So I think like we can kind of make it on like 1 or 2 sessions, like a collaborative thing, and like spend some time on it and come up with like a nice idea of how to present this combined together. That would be really nice. Any other idea? Well, I'd like to hear one thing about deep learning, that you know, now we saw like an introduction of different approaches in neural networks, right? It would be interesting to go through one example of like how we, you know, the challenges of the deep learning, to go through them, of like how we define like a set of combine a supervised method with an unsupervised, and build something in deep learning. But I think it would be also, we can also ask for people from GRAP for that too, or like
But
if we
there's
can
actually-
present.
This talk I'm doing here tomorrow, it's exactly on the idea that it would be good to have this kind of combination of unsupervised and supervised. But it's actually very supervised approach based. There's actually more how can you use it more in unsupervised, or make it as semi-supervised.
Yeah, actually, if we can put the
But the
information.
difficult thing for this was it's really hard to do deep learning on language, so you needed a big start. So I really wanted to kind of lay some of the foundations, so we can kind of talk further on. But for instance, when you talk about like workspace or word to vec, a lot of these kind of models are really excellent to use to plug into deep learning methods, because distributed semantics as such is not really deep. Well, it's at least one continuous space.
Yeah, I guess we browsed through it here at the end when you brought up the multilingual like possibilities. It's an area I've been very interested in before, and I still think it's like the holy grail of NLP in many senses. That like for
for each language you have to add the same amount of work. It's not like a very nice setup. So I would love to hear more on anything around that topic.
Have you worked on that?
Yeah, we did some stuff with the Codet where we tried to build models and try to put in machine learning or machine translated code to train kind of the same type of models.
I know some people working on that. Then, like maybe you can have again like a combined presentation.
It went terrible, so I don't know.
But that's an experience to learn, you know.
Yeah.
Okay, that would be nice. Any other suggestion, comments, anything? Yeah.
And about this workshop thing, something that's really nice is the Kaggle homepage, where you have these computer science or data science problems. And I don't know if there's something really small. Someone could introduce this and like showcase their approach to solving the Kaggle problem. It's really cool.
We had one of our ex-colleagues. He just moved to another company last year. He worked, if I'm not wrong, on an NLP problem in Kaggle, and he got also an award. And he had a kind of presentation related. So maybe I can get him to help us with that. And I guess there are many people that have experience with Kaggle. So just wave your hand if you can help. Yeah, it's a good idea. Okay, I know it is kind of late, but thanks a lot for coming. And yeah, sorry for some problems in the organizing of the events today. We try to improve, and hope to see you next time soon. Thanks.